Earth has a twin. Scientists have found worlds that match our size, our orbit, our distance from a star. One sits 24 million miles away, another sits 1,400 light-years out, and the closest one would take 75,000 years to reach at our fastest speed ever. We will visit all three. We will find out why the twin next door is almost impossible to reach, why the most perfect copy of Earth we have ever found is invisible to us in any real way, and why the universe has essentially built a wall around every world worth visiting. If you enjoy this journey, subscribe and leave a like. The scale of what we are about to cover will change how you see every star in the sky. Let's begin. For most of human history, people looked up at the night sky and assumed we were alone in our own solar system. One planet, one version of Earth. Then telescopes arrived, and everything changed. Venus appeared first. It glowed brighter than anything else in the sky besides the moon. It sat close. It matched Earth in size almost perfectly. Its diameter is only about 400 miles smaller than ours. Its gravity is 90% of what you feel standing on the ground right now. To every early astronomer pointing a telescope at the sky, Venus looked like a slightly smaller copy of home. The clouds made it even more exciting. A thick, white, unbroken layer of cloud wrapped the entire planet. You could not see the surface. That mystery sparked imagination. If clouds exist, maybe water exists. If water exists, maybe life exists. For centuries, serious scientists wrote about Venus as a likely tropical world. Warm, wet, possibly lush. Giovanni Schiaparelli, a respected Italian astronomer, spent years studying it in the late 1800s and believed the surface was covered in shallow seas. Other scientists agreed. They pictured something like a prehistoric Earth, steamy and ancient, buried under that permanent cloud cover. The cloud cover was the key detail everyone got wrong. Those clouds were hiding something, and what they hid was so extreme that when scientists finally got a good look, it redefined the word hostile. Venus does not orbit our star far away. At its closest approach, it sits roughly 24 million miles from Earth. For comparison, our moon sits about 239,000 miles away, so Venus is about 100 times farther than the moon. That sounds like a lot. On a cosmic scale, it is basically next door. That closeness made Venus the first target for the space age. The logic was simple. It is nearby. It looks like Earth. Go there, study it, understand how a twin world works. The first serious missions launched in the early 1960s, full of optimism. The results shattered every assumption built up over centuries. But here is the thing most people still do not realize. Even knowing what Venus actually is, even knowing it is a burning, crushed, acid-soaked disaster, scientists still call it Earth's twin. The surface destroyed the comparison. The basic structure of the planet did not. Venus and Earth formed from the same cloud of gas and dust around 4.5 billion years ago. They pulled in similar amounts of material. They ended up with similar mass, similar internal structure, similar distance from the center of the solar system in the early days of planetary formation. Twin planets, born from the same ingredients, shaped by the same early forces. So how did one become a paradise for life, and the other become the most hellish place we have ever confirmed exists? That answer took decades of research and dozens of missions to unravel. And it starts with something that sounds almost too simple. Venus spun the wrong way, rotated impossibly slowly, and trapped its own heat in a feedback loop that never stopped. A runaway greenhouse effect took hold billions of years ago and turned a world that might have had oceans into an oven. Scientists now believe Venus may have had liquid water on its surface for up to 2 billion years before something went catastrophically wrong. 2 billion years of potentially habitable conditions gone. The planet that looked most like home ended up being the most extreme warning about what Earth could one day become. And yet, even knowing all that, the distance to Venus still felt manageable. 24 million miles. Surely we could reach it. What scientists discovered when they actually tried was the first sign that distance in space is nothing like distance on Earth. For 300 years, the idea of a tropical Venus stuck around because nobody could prove otherwise. Astronomers watched it move across the sky. They measured its size. They tracked its orbit. They calculated that it sat close enough to our star to receive intense heat, but the bright clouds reflected so much of that energy back into space that early temperature estimates seemed almost reasonable. Some 19th century calculations suggested the surface might sit around 140 degrees Fahrenheit. Hot. Uncomfortable, still survivable in theory. Science fiction writers ran with it. Pulp stories from the 1930s and 40s filled Venus with jungles, dinosaurs, ancient civilizations, and hidden oceans. These stories felt plausible because the science of the time had not ruled them out. Even respected researchers speculated carefully about the possibility of life. Then radio telescopes arrived. In the late 1950s, astronomers started bouncing radio waves off Venus and measuring the return signal. What came back was alarming. The surface was radiating heat at a level that suggested temperatures far beyond anything previously imagined. The number that emerged stopped people cold, somewhere around 800 to 900 degrees Fahrenheit at the surface. That is hotter than most kitchen ovens set to maximum, hotter than the melting point of lead, hotter than the melting point of zinc, a temperature where metal turns liquid and pours across the ground. Nobody wanted to believe it at first. The readings seemed too extreme. Some scientists argued the radio signals were bouncing off the upper atmosphere and giving false readings, not representing the actual ground below. That debate lasted years. It ended on December 14, 1962. A spacecraft called Mariner 2 flew past Venus at a distance of about 20,000 miles and scanned the planet directly. Mariner 2 carried instruments designed to measure heat at different altitudes. When it passed the dark side of Venus, the side facing away from the star at that moment, temperatures still came in scorching. Both the daylight side and the dark side burned equally. The heat was not coming from direct radiation. It was trapped inside the atmosphere. The greenhouse effect was doing something on Venus that no model had fully predicted. Carbon dioxide in the atmosphere was behaving like a planet-sized blanket. Heat entered from the star, tried to escape back into space as infrared radiation, and got trapped by the dense gas layer above. The atmosphere itself had become a heat prison. Mariner 2 confirmed it. The romantic idea of a tropical Venus died in a single flyby. Soviet scientists took the next step. Their Venera program sent a series of probes directly into the atmosphere across the 1960s and 70s. The goal was to land on the surface and send back data. What they got instead was a brutal education in just how violent Venus truly is. The first probes were crushed before reaching the ground. The atmospheric pressure on Venus is 90 times greater than Earth's at sea level. Imagine diving to a depth of about 3,000 feet underwater. The pressure at that depth would kill an unprotected human in seconds. The Venusian atmosphere creates that same crushing force everywhere, at all times, across the entire planet. Engineers redesigned the probes to be stronger, thicker walls, pressure-sealed instruments. Venera 7 finally landed in 1970 and survived long enough to transmit data for 23 minutes before the heat destroyed it. 23 minutes was all the hardest metal and engineering of that era could manage. The paradise that generations of scientists and storytellers imagined was a 900-degree pressure cooker wrapped in acid clouds. And that description barely scratches the surface of how strange Venus actually gets. Venera 7 landed on December 15, 1970, and the scientists in Moscow waited. The probe had been built to survive conditions that would destroy almost anything humans had ever constructed. The shell was thick enough to handle the crushing pressure. The instruments were sealed. The engineers were confident the probe would last at least a few minutes on the surface. What they received was a faint, weak signal, barely detectable. The team almost logged it as equipment failure and moved on. Then one researcher, listening more carefully, realized the signal carried actual temperature data. The probe had landed on its side after impact, sending the antenna in the wrong direction. The signal was weak because it was bouncing off the ground at a bad angle, but it was real. 23 minutes of data from the surface of another world. The temperature reading came back at 887 degrees Fahrenheit. The pressure reading confirmed the surface sat under an atmosphere 90 times denser than Earth's. The probe then went silent. The heat had overwhelmed its systems completely. That 23-minute window changed how scientists thought about the entire inner solar system. Venus was not a failed Earth. Venus was a demonstration of how completely a planet could go wrong while still being built from the same raw materials. Later Venera probes improved the design. Venera 9, in 1975, sent back the first actual photographs from the Venusian surface. Scientists gathered around the monitor expecting to see flat, featureless rock. What they saw instead were sharp, angular boulders, fresh-looking geological formations, a landscape that had been shaped recently by volcanic activity, geologically speaking. Venus was alive underground. Its interior was still churning. Massive volcanic plains covered most of the surface. Scientists identified over 1,600 major volcanoes on Venus, more than any other planet in our solar system. Some of them may still be active today, pumping fresh sulfur dioxide into an atmosphere already thick with it. That sulfur dioxide rises into the upper atmosphere. It mixes with water vapor, and the combination produces sulfuric acid. Those beautiful white clouds that astronomers admired for centuries are made of tiny droplets of concentrated acid, floating in organized layers roughly 15 miles thick above the surface. Rain falls on Venus. It evaporates before reaching the ground because the lower atmosphere is too hot for liquid to survive. So Venus has acid rain that never lands. It falls, turns to vapor, rises, condenses again, and falls again in a permanent cycle of toxic precipitation that goes nowhere. A day on Venus lasts longer than a Venusian year. The planet rotates so slowly that the planet completes one full orbit around the star before it finishes one full spin on its own axis, and it rotates backward compared to most planets in our solar system. From the surface, the star would rise in the west and set in the east if you could see it through the clouds at all, which you cannot. Every measurement confirmed the same picture. Venus is Earth's size. Venus formed in the same neighborhood. And Venus became something that should end any casual assumption that closeness equals safety. We could see it. We could reach it with spacecraft. We had mapped nearly its entire surface with radar. And still, no human being had ever stood on it, or ever would, given what the environment would do to a human body in seconds. The most striking part of the Venera program was how long it took each probe to reach the surface after entering the atmosphere. Descent took about an hour. 1 hour of falling through acid clouds into a crushing, superheated void, and the probes survived barely long enough to confirm what was waiting at the bottom. That should have prepared scientists for the next surprise. Getting a spacecraft to Venus is hard enough. Getting one into a stable orbit around it is something else entirely. Here is a fact that bends the mind when you first hear it. Sending a spacecraft to orbit Venus requires almost as much fuel as sending one all the way out to Jupiter. Jupiter sits roughly 500 million miles from Earth at its closest. Venus sits 24 million miles away at its closest. The difference in raw distance is enormous. So why does the fuel cost come out nearly equal? The answer is gravity, momentum, and the hidden cost of slowing down. Every object in our solar system moves at a specific speed to stay in orbit around our star. Earth moves at roughly 67,000 miles per hour. That is the speed required to balance our star's gravitational pull at our distance. Move slower, and you fall inward. Move faster, and you drift outward. Venus orbits closer to the star than Earth. Because it sits in a stronger gravitational field, it moves faster. Venus travels at about 78,000 miles per hour around our star, faster than Earth. Tighter orbit, more speed. When a spacecraft launches from Earth, it carries Earth's orbital velocity with it. It is already moving at 67,000 miles per hour through space relative to the star, even before its engines fire. To travel outward toward Mars or Jupiter, it fires engines forward, adding speed, letting gravity from the star pull it into a wider arc that reaches those distant worlds. To travel inward toward Venus, it has to do the opposite. It fires engines backward. It sheds speed. It falls toward the star, curving down toward Venus's tighter orbit. But here is the trap. When it arrives near Venus, it is moving too fast. The spacecraft has been falling inward, accelerating the whole time. To enter a stable orbit around Venus rather than just flying past it, the spacecraft must fire engines again, this time to slow down dramatically. That double burn, shedding speed to go inward and then shedding more speed to enter orbit, eats through fuel at a rate that rivals an outer planet mission. Engineers call the total speed change required for a mission delta V, which stands for change in velocity. The delta V budget for orbiting Venus runs shockingly high. Think of it like driving a car down a steep mountain. You cannot just let gravity pull you down and arrive safely at the bottom. You have to brake constantly. Braking costs energy. On a mountain, your brake pads take the heat. In space, your rocket engines burn fuel to create that same slowing force. And unlike brake pads, fuel does not come cheap or weightless. Every kilogram of fuel a spacecraft carries adds weight. More weight requires more fuel to move. More fuel adds more weight. The problem compounds on itself. Engineers call this the tyranny of the rocket equation, and it makes every mission to the inner solar system brutally expensive in terms of mass. This is why hundreds of dead satellites and spent rocket stages orbit our star in the inner solar system. Many of them were sent on trajectories toward Venus or Mercury and ran out of fuel before they could match orbital speeds. They simply fly past their targets and keep drifting, silent, without enough energy left to do anything useful. A spacecraft with perfect fuel efficiency that launched today toward Venus would still need months of careful trajectory planning, multiple gravitational assists from Earth and other planets to pick up or shed speed, and a precisely timed engine burn at Venus arrival that has zero margin for error. All of that to reach a planet 24 million miles away, and yet, compared to what comes next in our search for an Earth twin, Venus might as well be across the street. Picture the solar system as a spinning drain. At the center sits our star, the most massive object in the neighborhood by a massive margin. Everything else circles it, because the star's gravity pulls every nearby object inward constantly. The reason planets do not spiral into the star and vanish is that they are all moving sideways fast enough that their inward fall curves into a continuous loop. They are perpetually falling but also perpetually missing. This motion creates something invisible but enormously powerful. Every planet carves its own lane through this gravitational field. Each lane runs at a different speed. Earth's lane moves at 67,000 miles per hour. Venus's inner lane moves faster. Mars's outer lane moves slower. Mercury's innermost lane is the fastest of all the rocky planets. Crossing between these lanes is not like changing lanes on a highway. On a highway, you ease the wheel slightly and move over. In the solar system, crossing between orbital lanes requires massive changes in velocity. You are fighting against a gravitational field that wants every object to stay in its specific lane at its specific speed. A spacecraft leaving Earth's lane has to be thrown into a special transitional path called a transfer orbit. A transfer orbit is an elongated ellipse, like a stretched oval, that connects two different lanes. The spacecraft travels along this oval path, coasting on its momentum until it reaches the other planet's lane. Getting onto a transfer orbit inward toward Venus requires slowing down relative to Earth. The spacecraft falls toward the star, follows the oval inward, and after roughly 3 to 6 months of coasting, arrives near Venus. The problem is that coasting inward accelerates the spacecraft. Gravity pulls it faster and faster as it approaches the inner part of the solar system. By the time it reaches Venus, it is moving too quickly for Venus's gravity to capture it naturally. A spacecraft approaching Venus at the wrong speed simply flies past. Venus pulls on it, curves its path slightly, and sends it off in a new direction. The spacecraft never stops. It just gets bent and released, continuing on its way through the solar system like a ball bouncing off a wall. To actually stop at Venus and enter a stable orbit, the engines must fire against the direction of travel, hard, for a long time, burning through the precious fuel carried all the way from Earth. Some spacecraft use a technique called aerobraking, where they dip into the top of Venus's atmosphere on purpose, using atmospheric drag to slow down gradually over many orbits. The atmosphere scrubs off speed like sandpaper. It is slower but cheaper in fuel cost. The problem is that Venus's atmosphere is also brutally hot even at high altitudes, and the spacecraft must survive repeated passes through acid-laced gases without melting. Every mission to Venus requires solving this problem in a new way. Every solution costs mass, fuel, or time, and usually all three. The gravity whirlpool does not care how close Venus is in miles, it only cares about velocity. And velocity, in the language of space travel, costs everything. This same physics problem scales up when you look further out. If reaching the closest failed twin takes this much effort, imagine what reaching a true Earth twin across the galaxy demands. The numbers stop being numbers, they become something else entirely. Speed is the currency of space travel. Every mission has a budget. On Earth, a travel budget measures money. In space, it measures speed change. Every burn of a rocket engine adds to or subtracts from the total speed of a spacecraft. Engineers track this carefully and call the total speed change needed for a mission the delta V budget. The unit sounds simple: speed, miles per hour, or meters per second. But the consequences of a delta V budget are enormous, because fuel does not just cost money. Fuel costs mass, and mass in space is the heaviest possible burden. Here is the core problem. A rocket carries fuel to move its payload, which might be a probe or a satellite or a crewed capsule. To move that payload, it needs a certain amount of fuel, but that fuel adds weight. To move that added weight, it needs more fuel. That extra fuel adds more weight, which requires still more fuel. The spiral keeps going, and engineers call it the tyranny of the rocket equation. For a mission to Venus orbit, the delta V requirement runs higher than most people expect. Getting to the Martian surface from Earth requires a certain level of speed change. Getting into orbit around Venus requires nearly the same amount, despite Venus being far closer in raw distance. That gap between expectation and reality comes down entirely to the fuel needed to brake against gravity and shed all that accumulated inward speed. The Voyager probes offer a useful comparison. They launched in 1977 and were designed for the outer solar system. Their trajectory used gravity assists from Jupiter and Saturn to fling them outward at high speed without burning extra fuel. Those assists are possible because outer planets are massive enough to significantly bend and accelerate a spacecraft's path. Venus, being smaller and sitting in a deeper gravitational field, offers less useful assistance for inbound trajectories. A spacecraft heading to Venus cannot pick up free speed the same way. Every bit of braking has to come from onboard fuel. This is why engineers sometimes route spacecraft to Venus in counterintuitive ways. Some missions fly past Venus not to stop there, but to use its gravity as a slingshot to reach somewhere else. Venus Express, a European mission, actually used multiple Earth flybys to build up the right trajectory before heading inward. The route that looks longest on a map is sometimes the cheapest in Delta V. A crewed mission to Venus, if one were ever attempted with today's technology, would require carrying enough fuel to decelerate into orbit and then accelerate back out again for the return journey. The fuel mass required would dwarf the rest of the spacecraft combined. Engineers have estimated the launch vehicle would need to be several times larger than any rocket ever built, just to carry enough propellant for a round trip. The crew would also face another problem. Time spent in deep space means time exposed to cosmic radiation, muscle loss in zero gravity, bone density decline, and the psychological strain of isolation. Venus is close enough that the round trip might take roughly 8 to 16 months depending on the launch window, long enough for serious health effects, short enough that it might still be survivable. Mars missions get far more attention, but Venus sits closer, and a crewed mission there would test every limit of current spacecraft design just as severely. The Delta V budget does not lie. Distance in miles is the wrong measurement. Speed change is the real price of space travel, and every world in our solar system charges a different rate. Imagine landing on Venus. You would have seconds, maybe less. The temperature at the surface averages around 870 degrees Fahrenheit. That is nearly 5 times hotter than a conventional oven at its highest setting. Exposed aluminum melts, lead pours like water, steel softens. Human tissue would not even get a chance to burn in the traditional sense. The heat would simply destroy it on contact. But temperature is not even the first problem. The first problem is pressure. The Venusian atmosphere presses down on the surface with 90 times the force of Earth's atmosphere. At sea level on Earth, the air around you pushes on your skin at about 14 pounds per square inch. On Venus, that number climbs to over 1,300 pounds per square inch. For comparison, that is the same pressure found roughly 3,000 feet underwater in Earth's oceans. No human diver goes to 3,000 feet. Submersibles designed specifically for deep ocean research, built from thick titanium and steel, can reach those depths, barely. A human body without that kind of protection would be crushed in an instant. The Venera probes that the Soviet Union sent to Venus were built like tanks, thick metal spheres with pressure-sealed instruments, and the heat still destroyed them within an hour of landing, 23 minutes for the earliest ones. The best lasted about 2 hours. Above the crushing surface, the clouds begin roughly 30 miles up. From there to about 45 miles altitude, the temperature drops to something closer to Earth-like, somewhere around 170 degrees Fahrenheit, and with atmospheric pressure similar to Earth at sea level. That zone is the most temperate place on Venus. Scientists have actually discussed the possibility of floating research stations kept aloft by the atmosphere at that altitude, well above the toxic surface. But floating above a planet is very different from living on one. The cloud layer itself is made of sulfuric acid droplets in concentrations that would eat through most materials over time. Even in that livable temperature band, the chemical environment would destroy equipment, corrode seals, and slowly consume anything humans sent into it. The wind at the surface of Venus moves slowly, only about 2 to 4 miles per hour, gentle almost. But because the atmosphere is so dense and heavy, even that slow wind pushes with tremendous physical force. Walking through it would feel like walking through slowly moving water, dense, pressing, constant. From the ground, the sky glows a dull orange red. Sunlight filters through layers of acid cloud and gets absorbed and scattered until it becomes a dim, even glow with no visible source. There are no shadows on the Venusian surface. The light comes from everywhere at once, flat and eerie. That landscape sits utterly still, except for wind and the occasional volcanic eruption. Recent data from multiple spacecraft suggests that Venus is geologically active right now, with eruptions happening somewhere on its surface within the last few years. Scientists have found evidence of a massive volcanic region about 1,000 miles across, where the ground appears to have been reshaped very recently in geological terms. Lava flows that look fresh, vent systems that appear active. Venus burns, it crushes, it corrodes, and under all of that, it churns. The planet that looked most like Earth from a distance turned out to hold almost every extreme condition known to planetary science. And yet, compared to the distances we have to cross to reach any true Earth twin, Venus might as well be a neighbor you could wave to from your front porch. Space around our star is full of ghosts. Hundreds of spent rocket stages, dead satellites, and abandoned probes drift in slow orbits through the inner solar system. Some were intentional disposals. Many were accidents. And a significant number of them ended up stranded because engineers underestimated one simple rule. Getting somewhere in space requires fuel, and running out of fuel in space means staying exactly where you are, forever. The inner solar system is particularly brutal for this reason. Because orbital lanes run fast and tight near the star, matching speeds with planets like Venus and Mercury demands enormous delta V. Probes sent toward those planets sometimes arrive with empty tanks. They fly past, unable to slow down, and join the silent collection of hardware circling the star on useless paths. The most famous example of this problem involves early missions to Mercury. Mercury sits closer to the star than Venus, which means its orbital lane runs even faster. Reaching Mercury and capturing into orbit around it is one of the most fuel-intensive missions in the entire solar system. A spacecraft heading from Earth toward Mercury might seem like it would just fall inward and arrive. The reality is the opposite. The spacecraft falls inward, gaining speed from the star's gravity, and arrives at Mercury moving far too fast to be captured by Mercury's relatively weak gravitational pull. Without a massive braking burn, it flies straight past. The Mariner 10 mission in the 1970s solved this, partly by using Venus as a gravitational brake. The spacecraft flew past Venus and used Venus's gravity to slow down and redirect its path toward Mercury. It still flew past Mercury 3 times and could never fully enter orbit. Only the Messenger spacecraft, decades later, managed to actually orbit Mercury, and it required multiple gravitational assists from Earth, Venus, and Mercury itself over a 7-year journey just to arrive slowly enough to be captured. 7 years to reach a planet that sometimes sits only about 50 million miles from Earth. Meanwhile, the outer solar system missions had it easier in some ways. The Voyager probes used Jupiter and Saturn's gravity to accelerate outward for free. New Horizons, which flew past Pluto, launched in 2006 and used Jupiter's gravity to shave years off its travel time. Going outward, gravity assists add speed. Going inward, they mostly help bleed it off. The collection of dead hardware in the inner solar system represents something larger than engineering failure. It represents the hard physical reality that proximity and distance means almost nothing in space travel. A probe sitting in orbit around Venus right now has done something more difficult, in terms of fuel cost, than a probe sitting in orbit around Saturn. Every spacecraft sent to Venus in the coming decades will face the same challenge. Engineers will plan trajectories years in advance. They will route missions through multiple flybys of Earth and other bodies to shape the path carefully. They will carry the absolute minimum mass possible to maximize fuel efficiency. And still, after all of that, the delta-V demands of Venus orbit will push every system to its design limit. The ghosts drifting through the inner solar system are proof of that. And if the inner solar system charges that much just to visit a neighbor, consider what happens when the destination is not 24 million miles away, but 4 light-years, a unit of distance so large that our fastest spacecraft would need 75,000 years to cross it. Venus failed the test. So what does passing it actually require? Scientists use a specific checklist when deciding whether a planet qualifies as a true twin of Earth. Size alone is not enough. Gravity alone is not enough. Even location relative to its star is not enough on its own. A true Earth twin needs to check multiple boxes at the same time, and each box represents conditions that allow liquid water to exist on a surface over long periods of time. The first requirement is size. A planet needs to be close enough to Earth's mass to hold a stable atmosphere without either losing it to space or crushing itself under its own weight into a gas giant. Scientists look for planets with a mass somewhere between half of Earth's and about twice Earth's. Within that range, the gravity is likely strong enough to keep gases close, but light enough not to compress them into something unbreathable. The second requirement is the habitable zone. Every star radiates a specific amount of energy. The habitable zone is the band of distance from that star where a planet receives enough heat to keep water liquid on its surface, assuming it has water and an atmosphere. Too close, and the water boils away. Too far, and it freezes permanently. Earth sits in our star's habitable zone. Venus sits slightly inside it, just close enough to tip the greenhouse feedback loop into catastrophe. Mars sits slightly outside it, cold enough that liquid water only exists in pockets underground, if at all. The third requirement is the type of star. Our star is a yellow dwarf, a stable middle-aged star that burns steadily without dramatic flares or explosions. Rocky planets orbiting more volatile star types, like red dwarfs, face constant bombardment from high-energy radiation that can strip atmospheres away over time. The fourth requirement is orbital stability. A planet that wobbles dramatically in its orbit, swinging close to the star and then far away in a long oval, would experience extreme temperature swings that make stable conditions difficult. Venus fails on the star type requirement, technically shares our star, but fails on atmospheric chemistry and greenhouse feedback. Mars fails on size and sits outside the habitable zone. Every other planet in our solar system fails on multiple categories simultaneously. The search for a true twin had to leave the solar system entirely. Astronomers turned their instruments toward other star systems, scanning thousands of planets detected by the Kepler Space Telescope over its 9-year mission. What they found among all those distant worlds was a planet that passed more of the checklist than anything detected before. A planet called Kepler 452b, sitting in a far corner of the Milky Way. It orbits a star almost identical to ours. It sits in the habitable zone. Its year lasts 385 days, just 20 days longer than Earth's. Its estimated size suggests a rocky surface is possible. On paper, it is the closest match to Earth ever confirmed. In practice, the distance to it makes every problem with Venus look like a short commute. Before the Kepler Space Telescope, almost everything known about exoplanets was theoretical. Astronomers had discovered a handful of planets orbiting other stars by the late 1990s, but those early detections mostly revealed giant worlds, gas planets the size of Jupiter or larger, orbiting extremely close to their stars, scorching massive objects on fast orbits. Nothing like Earth. Nothing like any place a person could imagine standing on. The detection method of the time required it. Scientists tracked the wobble a planet causes in its star. When a planet orbits a star, its gravity tugs the star slightly back and forth as it moves. By watching a star's light carefully and measuring tiny shifts in its wavelengths, astronomers could calculate whether something was pulling on it. Bigger planets cause bigger wobbles. Smaller planets, especially rocky Earth-sized ones, cause wobbles too small to detect with the instruments available. Kepler changed that. The spacecraft launched in March 2009 and immediately began watching a patch of sky containing roughly 150,000 stars simultaneously. Its method was different. Kepler watched for transits, the slight dimming of a star's light when a planet passes in front of it from the telescope's point of view. When a planet crosses its star, it blocks a tiny fraction of the star's light. For a large planet, the dimming might be 1% of the star's total brightness. For an Earth-sized planet, it might be 1/100th of 1%, a change so small it required the precision of space-based instruments to detect far above the blurring effects of Earth's atmosphere. Kepler measured the brightness of each of those 150,000 stars every 30 minutes, continuously, for years. Every time a star dimmed in a regular pattern, scientists flagged it as a possible planetary transit. Teams of astronomers then analyzed each flag, ruling out false positives from other causes and confirming real planets. The mission worked beyond anyone's expectation. Over its lifetime, Kepler detected over 2,700 confirmed exoplanets and thousands of additional candidates awaiting confirmation. For the first time, humanity had a realistic picture of how common planets are throughout the galaxy. The answer was staggering. Planets are everywhere. Virtually every star appears to host at least one. Many host several. The Milky Way alone contains hundreds of billions of planets, more than one for every single star in the galaxy. Among all those detections, Kepler's most celebrated find came in July 2015. Scientists announced the discovery of a planet in the Cygnus constellation, one that stood apart from everything else in the dataset. This planet orbited a star nearly identical to ours in size, temperature, and age. Its orbit placed it squarely in the habitable zone. Its orbital period suggested a year lasting 385 days. The team called it Kepler 452b. Newspapers called it Earth's older cousin. Scientists were more careful. They said it was the most Earth-like exoplanet ever found in the habitable zone of a Sun-like star. Most Earth-like. And still, when the celebration quieted, someone ran the numbers on distance. The number that came back silenced the room. Kepler 452b passed more tests than any exoplanet before it. Scientists spent months after the July 2015 announcement checking their work. The planetary data was solid. A planet orbiting a yellow dwarf star, the same class as ours, with a year almost identical in length to Earth's. The star itself burns about 10% brighter than ours and sits about 1.5 billion years older, meaning this system has had more time to develop than our own. The size estimate for Kepler 452b put it at roughly 1.5 times the diameter of Earth. That is larger. A planet that size could be rocky like Earth, or it could have accumulated enough mass to trap a thicker atmosphere and become something denser and heavier underfoot. Scientists call worlds in that size range super-Earths, a term that describes their size relative to Earth, but says nothing about whether they are habitable. The key detail that set Kepler 452b apart from other super-Earths was its location. It orbits inside its star's habitable zone, at the right distance for liquid water to exist on a surface with a functioning atmosphere. Many of the super-Earths Kepler discovered sat too close to their stars, baking in intense heat. Others sat too far out, frozen and dim. Kepler 452b sat right in the middle of the zone, the same position Earth occupies relative to our own star. Its orbital period of 385 days meant it circles its star in almost exactly the same time it takes Earth to complete one full orbit. A year there feels almost calendar compatible with a year here. That single fact made Kepler 452b feel real in a way that most exoplanets do not. A year of 385 days is something a person can picture. 365 days with 20 extra. Spring, summer, fall, winter. And then a slightly longer wait before it starts again. Scientists calculating the surface gravity estimate for this world came up with roughly twice Earth's gravity if the planet is rocky. That is significant for any discussion of life. Standing on its surface would feel like carrying your own body weight as a backpack, constantly with every step. Running would be exhausting. Jumping would barely lift you off the ground. Over thousands of generations, life adapted to that gravity would likely develop differently than life on Earth. That is all assuming life ever got a foothold there. Kepler 452b's star has been burning for 6 billion years. For context, Earth formed about 4.5 billion years ago, Life appeared here roughly 3.5 to 4 billion years ago. If the same timeline applied to Kepler 452b, complex life there could have had a 1.5 billion year head start on us. Sit with that. A civilization or an ecosystem that started 1.5 billion years before anything on Earth ever crawled out of the water. Scientists flagged that possibility immediately. They also flagged the uncertainty. Nobody knows what the surface of Kepler 452b looks like. Nobody knows whether it has water, an atmosphere, or any of the conditions life requires. The data confirms orbital parameters. Everything else remains an educated guess. What it is not a guess about is the distance. That number is precise, confirmed by multiple measurement methods. And that number is where everything about Kepler 452b stops being exciting and starts being something heavier. 1400 light years. Write it out and it looks manageable. 1400. That is how far you would drive if you crossed the United States from New York to Denver and kept going another 100 miles or so. Easy to say. Easy to write. The light year is where it breaks apart. 1 light year is the distance light travels in a full year. Light moves at 186,000 miles per second. Every second, a beam of light covers a distance that would take a car traveling at 60 miles per hour roughly 3.5 years to complete in 1 second, every second, without slowing down. Over a full year, moving at that speed constantly, light covers about 5.9 trillion miles. That number is written out as 5, followed by 12 zeros, a trillion miles, nearly 6 of them in a single year. 1400 light years means 1400 times that number. Take 6 trillion miles and multiply it by 1400. The result is a distance so large that most calculators struggle to display it without switching to scientific notation. But raw numbers are useless without something to compare them to. Here is a comparison that might help. The entire distance from Earth to our moon is about 239,000 miles. The distance from Earth to Kepler 452b is so much larger that if you laid the Earth to Moon trip end to end, you would need to repeat that journey roughly 35 quadrillion times before you finished crossing the gap. A quadrillion is 1,000 trillions. Light itself needs 1400 years to make that crossing. Not a spacecraft, not a rocket. The fastest thing in the universe, moving at 186,000 miles every second of every minute of every hour, takes 14 centuries to get there. Every image captured by a telescope of Kepler 452b shows the planet as it was 1400 years ago. In 1400 years, that planet has continued orbiting. Its star has continued burning. Oceans might have evaporated or appeared. Continents might have shifted. Whatever was there in 625 AD, the year the light we see today left that planet, is what our telescopes show. We are looking at history, ancient history. Whatever Kepler 452b looks like right now in this moment, we will not see it until the year 3426. The light carrying that image has not even left the planet yet. This is not a philosophical point. It is a physical one. Distance and time are the same thing when dealing with light. 1400 light years away means 1400 years out of date, with no way to get a fresher view. Scientists confirmed the planet exists by watching repeated transits, the planet crossing in front of its star from our line of sight. Those crossings still happen like clockwork. The planet is still orbiting, the star is still burning, but the snapshot we have of it is over a millennium old. And crossing that distance in person, that calculation leads somewhere that feels less like science and more like staring into something that does not end. Every time an astronomer points a telescope at Kepler 452b, they are performing a kind of time travel. The light arriving at the telescope right now left that planet over 1400 years ago. It has been crossing the galaxy the entire time, moving at the maximum speed physics allows. and it is only just arriving here. The information it carries is ancient. Whatever it tells us about Kepler, 452b describes conditions from the early 7th century. In 625 AD, the Byzantine Empire controlled much of what is now Turkey and the Middle East. The Tang dynasty was rising to power in China. Islam was in its earliest years. The printing press would not be invented for another 800 years. Nobody on Earth had any idea that photons of light were departing a distant planet at that exact moment, carrying a picture that would eventually be captured by a space telescope orbiting a world those photons would take 14 centuries to reach. That is what astronomers are studying. A snapshot frozen in the early 7th century, transmitted at the speed of light, now finally decoded by instruments we built in the 21st century. The planet itself does not care. It has kept orbiting for 1400 more years since that light left. Its atmosphere has continued whatever chemistry it was running. Its star has continued fusing hydrogen in its core. Anything on the surface, if anything exists there, has continued living, dying, evolving, or going extinct, completely unaware that a species 1400 light-years away is squinting at a 14 centuries old photograph of their world. This creates a strange situation for scientists. Confirming a planet exists in the habitable zone is one achievement. Knowing whether that planet is currently habitable, meaning right now in the actual present moment, is impossible. Even if Kepler 452b had a thriving biosphere in 625 AD, that biosphere could have been wiped out by a catastrophic asteroid impact 600 years ago, and we would not know for another 800 years. The news would not arrive for 8 centuries. The universe enforces information delays based on distance. The farther away something is, the older the information you receive about it. At 24 million miles, Venus shows us a picture that is about 2 minutes old. Our moon shows us a picture about 1.5 seconds old. The nearest star beyond our own shows us a picture about 4 years old. And Kepler 452b shows us a picture over 14 centuries old. There is no way around this delay. It is not a technology problem. It is a physics problem. Nothing carries information faster than light. No future invention will change that fundamental rule of the universe. Scientists deal with it by studying what they can confirm: orbital period, estimated size, star type, position in the habitable zone. All of those measurements describe the planet's situation in a way that changes slowly over geological time, so a 1400-year lag does not dramatically affect the core conclusions. But for the question that matters most, whether anything lives there, the universe simply refuses to answer. The delay is too long, the distance is too great. We see the past and call it discovery. And if seeing it is this complicated, imagine trying to go there. The Voyager 1 spacecraft launched in September 1977. It is the most distant human-made object in history. Right now it sits over 14 billion miles from Earth, deeper into interstellar space than anything else humanity has ever sent. It is moving at roughly 38,000 miles per hour, which sounds fast until you put it next to what it would need to accomplish. At that speed, traveling to Kepler 452b would take approximately 25 million years. Read that again slowly: 25 million years. To give that number any meaning, consider what 25 million years represents in Earth history. 25 million years ago, the Himalayas were still rising. Antarctica was beginning to freeze over permanently. Grasslands were spreading across the continents for the first time. Whales were evolving from four-legged land animals back into ocean swimmers. Humans would not exist for another 23 million years. A spacecraft launched today toward Kepler 452b at Voyager's speed would arrive at a destination where Earth has completely transformed. The continents would have shifted. Species that exist now would be gone. New ones would have evolved and possibly disappeared. Our star itself, over that immense time frame, would have visibly aged. The civilization that launched the spacecraft would have no meaningful way to track it, receive signals from it, or care about its findings. The people alive today, their children, their children's children, for 1,000 generations, and then 10,000 more generations, would all live and die long before the spacecraft crossed even a fraction of the distance. At Voyager's speed, 1,400 light-years takes not 1,400 years, but over 8,000 times longer than the current age of human civilization. The oldest writing humans have ever produced dates back roughly 5,000 years. The journey to Kepler, 452b, at current speeds would require a period of time 5,000 times longer than that. This comparison breaks the scale. Nothing in human experience prepares anyone for reasoning about 25 million years of continuous travel. And Voyager is humanity's fastest long-distance traveler. The Parker Solar Probe achieved higher speeds briefly during close passes by our star, reaching over 400,000 miles per hour. At that record-breaking speed, the trip to Kepler, 452b, still takes about 2 million years. 2 million years is the better number only by comparison. It is still an incomprehensible amount of time. Anatomically modern humans have only existed for about 300,000 years. A 2 million year journey is nearly 7 times longer than the entire history of our species. Every number generated by applying current spacecraft speeds to interstellar distances collapses into the same result: unreachable, not within decades, not within lifetimes, not within civilizations. Kepler 452b exists. Astronomers have confirmed that with multiple independent methods, it orbits its star, it sits in the right zone, it is the right size, and it might as well be on the other side of a locked door with no key, no door handle, and no way to even knock. The universe does not care about what we want. It built its distances first and let curiosity arrive later. But there is a world that is closer, much closer. Close enough that some engineers believe reaching it within a human lifetime might actually be possible. The catch is what that world is hiding underneath its potential. Numbers this large stop feeling real very quickly. 25 million years, the brain processes it as just a big number. It loses its weight, so let's build it piece by piece until the weight comes back. 1 million years ago, a human ancestor called Homo erectus was walking across Africa and Asia, using fire, shaping stones into tools, and spreading across a continent. That was 1 million years, 1/25th of the journey to Kepler, 452b. 5 million years ago, the ancestors of modern humans had not yet separated from the ancestors of chimpanzees. The lineage that would eventually produce every person alive today had not yet branched into its own path. That is 5 million years, still only 1/5 of the distance. 10 million years ago, the Alps in Europe were still actively rising. The Sahara was sometimes a lush grassland. Sea levels sat different from today. That is 10 million years, less than halfway. 20 million years ago, Antarctica was not fully covered in ice. The planet's climate ran warmer overall. Whales had already returned to the ocean but looked quite different from modern species. 20 million years, nearly there in the count, still 5 million short. 25 million years ago, our star sat in a slightly different position relative to the galactic center. The galaxy itself looked recognizably similar, but had experienced entirely different stellar events. Every species alive on Earth at that moment is now extinct, replaced by descendants that are themselves mostly extinct, replaced by their own descendants in a chain of change that produced everything visible in nature today. A spacecraft launched toward Kepler 452b at Voyager speed would return from its journey, if it could return, to a planet where humans may no longer exist in any recognizable form. Evolution does not stop. Species do not wait. 25 million years of biological change operates on a scale that produced everything from the mouse to the elephant. There is another layer to this. Every hour the spacecraft travels, it moves roughly 38,000 miles farther from Earth. After 1 year, it sits about 330 million miles from home. After 10 years, 3 billion miles. These distances sound large but are nothing on galactic scales. After 100 years, it sits about 30 billion miles out, still inside our own solar system's outer reaches. To cross the first light year of the journey alone takes roughly 17,000 years at Voyager speed. 1,400 light years means crossing that first increment 1,400 times over. Each increment alone is 17 millennia. The human mind has a useful defense mechanism. When numbers exceed a certain size, the brain simply stops generating the appropriate emotional response. Researchers who study risk and scale have confirmed this. A number too large to visualize receives the same emotional weight as a slightly smaller large number. Both feel like a lot. The difference between 25 million years and 2 million years does not register as 13 times worse. It registers as similarly vast. That failure of imagination is partly why the distance to exoplanets does not produce the panic it probably should. We are stranded here, on this planet, by distances our minds cannot process. And the nearest candidate that might be a true twin sits 1,400 light-years away, while an even closer candidate, only 4 light-years out, waits with its own surprises. Right now, light is leaving Kepler 452b and heading toward Earth. That light will travel at 186,000 miles per second for 1,400 years before it arrives here. When it does, telescopes on Earth or in orbit will capture it, and scientists will learn something about what that planet looked like 14 centuries from now. What they see will describe conditions during the 26th century, the early stages of whatever comes after our current era, a 1,400-year delay in the news, arriving in the future, showing the past. This loop of cosmic time delays applies to everything visible in the night sky. Every star seen is a historical artifact. The star system Kepler 452b belongs to appears in our sky as it was over 1,000 years ago. For all telescopes can confirm today, that star could have changed dramatically. Stars do not blow up often, but they do change. They grow brighter as they age. They shift positions slightly over millions of years as they orbit the galactic center. But scientists using the current snapshot, the one available today, have built a remarkably detailed picture from limited data. Kepler 452b's star is about 4% wider than ours and burns about 10% more brightly. That extra brightness is compensated by the planet's slightly larger orbital distance, keeping it inside the habitable zone. Over time, as the star continues to age and brighten, the habitable zone around it will shift outward. Scientists believe the planet is approaching the inner edge of that zone, meaning it may be heading toward a Venus-like runaway greenhouse future of its own. If that process is already underway, the planet may currently be experiencing rising temperatures, increasing atmospheric pressure from evaporating water, and growing cloud cover. The picture 1,400 years ago might have captured the last stages of a habitable world tipping toward instability, or it might have captured a stable world with billions of years of habitability remaining. The data available cannot distinguish between those two possibilities with current technology. This uncertainty is one of the most honest things about modern exoplanet science. Scientists found the most Earth-like world known to exist beyond our solar system, and the information they have about it is simultaneously remarkable and maddeningly incomplete. They know the orbital period, confirmed. They know the star type, confirmed. They know the estimated planet radius, reasonably confirmed from transit depth measurements. They do not know the surface conditions, atmospheric composition, actual temperature, presence of water, or any detail that would determine habitability in a meaningful way. Future telescopes, particularly large space-based instruments designed to collect and analyze the light that passes through a planet's atmosphere during transit, might eventually detect chemical signatures in Kepler 452b's atmosphere: oxygen, methane, water vapor, combinations of molecules that suggest biological activity. But those measurements would still come from light that is 1400 years old. Any discovery would describe conditions from the 21st century to anyone born in the 35th century, when the light with that information finally arrives back at Earth after being sent in response to any future signal we might transmit. The planet waits, the light travels, the universe keeps its own schedule with no interest in ours. 1400 light-years of distance hides a surface that might never be seen clearly. Every image taken of Kepler 452b is essentially a shadow. Scientists detected the planet by watching it pass in front of its star and measuring the tiny dip in the star's brightness. That dip told them the planet exists, and the size of the dip told them roughly how large the planet is. But the planet itself, the actual rock or gas or ocean that makes up its body, remains invisible. No telescope ever built has directly photographed Kepler 452b. The planet is far too small and far too distant to resolve as anything other than a mathematical inference from light curves. It is a pattern in data, confirmed by its repeated appearance as the planet completes orbit after orbit. The planet is real. What it looks like, nobody knows. This creates a specific kind of scientific frustration. Scientists have enough data to name the planet, describe its orbital parameters, estimate its size, and calculate where it sits in the habitable zone of its star. They do not have enough data to determine whether it has a solid surface. That last point is crucial. A planet 1.5 times Earth's diameter could be rocky, meaning it has a crust, a mantle, a solid surface where something could theoretically stand. Or it could be a small gas planet, sometimes called a gas dwarf or a mini Neptune, that has no surface at all. Under its thick atmosphere might sit just denser and denser layers of gas, until the pressure eventually forces the gases into a liquid state at the core. Earth is a rocky planet. Mars is rocky. Venus is rocky. Jupiter is a gas giant with no surface to stand on. Kepler 452b sits in a size range where either outcome is physically possible, and the transit data alone cannot distinguish between them. To determine whether a planet is rocky or gaseous from a transit measurement, scientists need to know its density. Density requires knowing both the size and the mass. Size comes from the transit depth. Mass requires measuring the gravitational wobble the planet causes in its star over time, a technique called radial velocity measurement. For Kepler 452b, the star is distant enough and the planet small enough that the wobble it causes falls below the detection limit of the instruments used to confirm it. The mass is unknown, the density is therefore unknown. Rocky or gaseous remains an open question. Scientists make probabilistic arguments. At 1.5 times Earth's diameter, statistical models suggest the planet is more likely rocky than gaseous, since smaller planets in this size range tend to be rocky based on data collected from many other planetary systems. More likely is not confirmed. The surface of Kepler 452b remains hypothetical. If it is rocky, the surface gravity is estimated at roughly twice Earth's. Every step on that surface would feel heavy and slow. Mountains would likely sit lower relative to the planet's size because higher gravity compresses geological formations. The atmosphere might be thicker, denser, more pressure-filled than Earth's, which would make the sky darker and the weather patterns more extreme. If it is gaseous, there is no surface, no ground to stand on, no place to build anything, just an endless descent through thickening atmosphere until the pressure becomes fatal, then past that into liquid and eventually into a crushing core. And all of this description of a world that humanity can never visit, at least with any technology conceivable today, describes something 1400 years in the past. The real surface of Kepler 452b right now, in this moment, sits unreachable and unseen, behind a wall of distance that no road, ship, or rocket in human history has ever come close to crossing. The universe hid its most Earth-like world behind the largest possible lock. And for most of human history, we did not even know the lock existed. For decades, the search for an Earth twin pointed outward toward distant constellations. Kepler 452b sat 1,400 light-years away. Other candidates discovered by the Kepler mission sat even farther. The universe seemed determined to place every interesting world beyond any practical reach. Then in August 2016, a team of astronomers announced something that changed the conversation entirely. A planet orbiting the closest star to our solar system, 4.2 light-years away. The star is called Proxima Centauri, and it sits so close in galactic terms that astronomers sometimes describe it as our nearest stellar neighbor. If the entire Milky Way galaxy was shrunk down to the size of North America, the distance from our solar system to Proxima Centauri would be about the width of a single sheet of paper. That is close. Cosmically speaking, absurdly close. The planet orbiting it received the name Proxima Centauri b, and the announcement of its discovery generated more excitement in the astronomy community than almost anything since the confirmation of gravitational waves earlier that same year. Scientists around the world ran the initial numbers and found something remarkable. The planet sits inside the habitable zone of its star. Its mass is estimated at slightly more than Earth's. Its orbital period is only 11 days, but that short year reflects the fact that it orbits extremely close to a very dim star, not that it is receiving too much heat. The confirmation came after years of careful observation. A team using telescopes in Chile spent extensive time watching Proxima Centauri's light for the telltale wobble that indicates a planet pulling on it gravitationally. The signal was there, repeating, consistent, real. For the first time in history, humanity had confirmed a potentially habitable world at the nearest star to our own. The reaction was electric. Scientists who had spent careers arguing that interstellar travel was a fantasy of science fiction suddenly had a specific destination with a confirmed address. Engineers began dusting off old theoretical proposals for deep space propulsion. Space agencies discussed what a mission towards Proxima Centauri might look like in the distant future. 4.2 light-years felt different from 1,400. It still represented an almost incomprehensible distance, but it was at least a distance that some proposed technologies might one day approach in terms of travel time. A journey measured in decades rather than millions of years suddenly seemed to exist somewhere in the realm of extreme possibility rather than pure fantasy. But Proxima Centauri b came with complications. The star it orbits is nothing like ours, and the conditions that planet faces every single day are unlike anything Earth has ever experienced. The star tells a story that the planet has to live with, and that story is brutal. 4.2 light-years sounds small compared to 1,400. It is smaller, but converting it to miles reveals a number that still collapses under its own weight. 1 light-year equals about 5.9 trillion miles. 4.2 light-years equals roughly 25 trillion miles. Written out fully, that is 25 followed by 12 zeros, 25 million miles. A number so large, it has no practical frame of reference in human daily life. Try building one anyway. The distance from New York City to Los Angeles is about 2,800 miles. To cover 25 trillion miles using that trip as your unit, you would need to make the New York to Los Angeles drive roughly 9 trillion times. If you drove that route every single day without stopping, it would take you about 25 billion years. The universe itself is only about 14 billion years old. Try another comparison. The distance from Earth to our moon is about 239,000 miles. To reach Proxima Centauri b, you would need to travel the Earth-to-Moon distance roughly 105 million times in a row. The fastest human-made object ever created in terms of sustained travel speed is the Voyager 1 spacecraft, moving at roughly 38,000 miles per hour. At that speed, covering 25 trillion miles, takes approximately 75,000 years. 75,000 years ago, modern humans were living in small groups across Africa and parts of Europe and Asia. Cave paintings had not yet been created. Agriculture did not exist. Written language would not appear for another 70,000 years. Everything that constitutes human civilization, every city, every language, every invention, every war, every discovery, happened within a fraction of the time it would take a Voyager-speed spacecraft to reach Proxima Centauri b. 75,000 years of travel. For the closest star, some proposed spacecraft designs aim to do better. Advanced ion drives, nuclear pulse propulsion, and other theoretical systems might push a robotic probe to speeds several times higher than Voyager's. Even at 10 times Voyager's speed, the journey still takes 7,500 years, multiple human civilizations rising and collapsing within a single transit time. The number 4.2 light-years feels intimate compared to 1400. It feels like something that might one day be crossable. The conversion to miles and then to travel time reveals the deception. 4.2 light-years is still a chasm that would consume every generation of humanity alive today and most of the generations that will follow. And Proxima Centauri b has to earn that effort. A world that far away, reached at that cost, needs to actually be worth arriving at. What awaits any probe or crew that eventually makes it there is not what most people picture when they imagine a habitable world. Proxima Centauri is a red dwarf star. Most stars in the Milky Way are red dwarfs. They are smaller, cooler, and dimmer than yellow stars like ours. Because they burn more slowly and conservatively, they live far longer. A red dwarf can burn steadily for trillions of years, far longer than the current age of the universe. In theory, red dwarfs create the most stable long-term stellar environments possible. In practice, they are among the most violent hosts a planet can orbit. The issue is magnetic activity. Red dwarfs generate powerful and erratic magnetic fields. These fields twist and snap unpredictably, releasing enormous bursts of energy called stellar flares. A stellar flare from a red dwarf can be hundreds of times more powerful than any flare ever recorded from our own star. Proxima Centauri is particularly active. It flares constantly. Scientists monitoring it have recorded flares powerful enough to briefly increase the star's brightness by factors of 10, 50, or even more within minutes. These events release massive amounts of ultraviolet radiation and X-rays. Proxima Centauri b orbits its star at roughly 5% of the distance Earth orbits ours. It sits that close because the star is so dim that a planet needs to be very near just to receive enough warmth for liquid water. That closeness means the planet sits directly in the path of every flare, every burst of radiation, every surge of charged particles the star throws out. Earth receives a certain baseline level of X-ray radiation from our star. Proxima Centauri b receives about 400 times that amount every single day, averaged across flare and quiet periods combined. During major flare events, the radiation spike can be thousands of times Earth's normal level for minutes at a time. What does that level of radiation do to a planet? It strips atmospheres, high-energy particles from stellar flares, slam into atmospheric molecules, and give them enough energy to escape the planet's gravity. Over millions of years of constant bombardment, an atmosphere can be gradually sanded away into space. Mars lost much of its atmosphere through a similar process after its magnetic field weakened billions of years ago. Proxima Centauri b faces a far more aggressive version of that same stripping force every single day. Whether the planet has retained an atmosphere depends on factors scientists cannot yet measure directly. A strong planetary magnetic field, generated by a rotating liquid iron core, can deflect many of the incoming charged particles. Earth's magnetic field does exactly this, creating the auroras visible near the poles, as a side effect of that deflection. If Proxima Centauri b has a strong magnetic field, it might have held onto enough atmosphere to matter. If its core cooled and solidified early, losing the magnetic field, the atmosphere was likely stripped down to almost nothing long ago. Scientists do not know which scenario applies. The question remains open. But the radiation environment alone makes Proxima Centauri be a far more complicated candidate than its habitable zone location might suggest, and the radiation problem is only the beginning of what makes this world strange. Every atmosphere in the solar system has a story about how it survived. Earth's atmosphere persists because of a combination of factors working together. The planet's gravity is strong enough to hold gas molecules close. The magnetic field deflects the most energetic particles from our star. The geology continuously replenishes gases through volcanic activity. The chemistry of the atmosphere cycles through reactions that keep the overall balance stable. Remove any one of those factors and the atmosphere begins to degrade. Proxima Centauri b faces the atmosphere stripping problem on a scale that dwarfs anything in our solar system. The stellar flares arriving at this planet carry charged particles moving at high fractions of the speed of light during major events. These particles do not just knock atmospheric molecules away gently, they hammer into the upper atmosphere with enough force to ionize gases, heat entire atmospheric layers, and accelerate molecules past escape velocity in surges. Computer models built by atmospheric scientists to simulate this process give troubling results. When researchers run simulations of a planet with Earth-like atmospheric composition exposed to Proxima Centauri's actual flare history, the planet loses its nitrogen and oxygen within hundreds of millions of years. For comparison, Earth's atmosphere has existed in roughly its current form for over 2 billion years. Some models suggest that a planet with a very strong magnetic field could retain atmosphere significantly longer, perhaps long enough to matter for habitability. The uncertainty comes from not knowing what Proxima Centauri b's interior looks like. Is there a liquid iron core spinning fast enough to generate a protective magnetic field? Nobody can measure that from here. There is an additional wrinkle. Even if the planet retained an atmosphere, that atmosphere would bear little resemblance to Earth's. Constant irradiation drives chemical reactions in the upper atmosphere that break apart molecules and reform them into different compounds. An atmosphere shaped by 400 times Earth's normal X-ray exposure over billions of years would likely contain compounds produced by that high-energy chemistry, potentially toxic ones, in concentrations that make the air poisonous, even if the pressure and temperature feel manageable. Scientists have also considered a different possibility. Some research suggests that planets orbiting red dwarfs might develop extremely dense carbon dioxide atmospheres through geological outgassing, particularly if the initial water content was high. A thick carbon dioxide layer can actually provide some shielding against certain types of radiation, as the dense gas absorbs and scatters incoming energy. Venus has a thick carbon dioxide atmosphere, and while Venus is catastrophically hot, its surface is shielded from certain kinds of space radiation by that same dense layer. A Proxima Centauri b with a Venus-like carbon dioxide atmosphere would be terrible for life as known on Earth, but it might have survived the radiation environment better than a planet with a thin nitrogen-oxygen atmosphere. The atmosphere question sits at the center of everything unknown about this world. An atmosphere determines temperature, pressure, radiation exposure at the surface, weather patterns, and chemistry. Lose it, and the planet is a bare rock. Keep it, and the planet might be livable. The answer to which scenario happened is sitting 4.2 light-years away, hidden from every instrument humanity has built so far. Proxima Centauri b orbits its star every 11 days. That 11-day orbit sits extremely close to the star, close enough that a powerful gravitational effect called tidal locking almost certainly applies to this world. Tidal locking happens when a massive body's gravity grabs onto a smaller orbiting body and synchronizes its rotation with its orbit. The same process happened with Earth's moon. The moon takes about the same amount of time to rotate once on its axis as it takes to orbit Earth. The result is that the same side of the Moon always faces Earth. The far side of the Moon, the side facing away from us, was completely unknown until spacecraft flew around it for the first time. Proxima Centauri b sits close enough to its star that the same thing almost certainly happened there. One side of the planet faces the star permanently. One side faces away permanently. There is no day-night cycle. There is a permanent day side and a permanent night side. The day side bakes. Even though Proxima Centauri is a dim red star, sitting that close means the day side receives intense heat continuously, with no night to cool things down. Surface temperatures on the day side could reach levels far above what complex chemistry requires for stability. The night side freezes, with no star ever rising above the horizon on that side of the planet. Heat comes only from internal geological processes, or from circulation of atmosphere from the day side. Without a thick atmosphere to transport heat efficiently, the night side could cool to hundreds of degrees below zero, cold enough to freeze carbon dioxide out of the atmosphere entirely. Between the permanent day and permanent night sits a thin ring of territory called the terminator zone. This is the line where day meets night, where the star sits perpetually on the horizon, neither fully risen nor fully set. In this band, temperatures might sit in a range that allows liquid water under the right atmospheric conditions. Some scientists have proposed that life, if it ever developed on Proxima Centauri b, might cluster in this thin habitable strip. A world not like Earth, where habitable conditions cover the entire globe, but a world where the livable zone is a narrow ring of eternal twilight. That is a deeply alien picture. A civilization on such a world would never experience a sunrise or a sunset. The star would sit fixed on the horizon from the perspective of anyone in the terminator zone. One direction would lead into blinding heat, the other direction into lethal cold. Everything worth having would exist in the thin band between extremes. Whether that strip could sustain an atmosphere, whether liquid water could persist there, and whether any form of life found a foothold in it are questions that current instruments cannot answer. What can be said is that even in the most optimistic scenario for Proxima Centauri b, the planet is profoundly different from Earth. Habitable does not mean familiar, and getting there to check for yourself takes so long that the word getting there barely applies. A crewed mission to Proxima Centauri, be at any speed achievable with current technology, is not a mission, it is a sentence. 75,000 years of travel, in a sealed metal container, in complete darkness between the stars, with no resupply possible from Earth, no rescue if something fails, and no destination confirmed to be worth arriving at. The 75,000-year figure assumes Voyager-level speeds, the fastest sustained velocity humanity has ever achieved in deep space travel. Engineers working on advanced propulsion concepts have suggested nuclear thermal rockets might achieve speeds 2 to 4 times higher than Voyager. That would reduce the journey to somewhere between 20,000 and 35,000 years. Still measured in tens of thousands of years, the psychological challenge alone is staggering. Humans evolved as social creatures in small groups with sunlight, seasons, horizons, and constant environmental change. Every sensory input that shaped human psychology over hundreds of thousands of years of evolution would be absent on an interstellar voyage. The crew would live in a cylinder. The stars outside would barely appear to move over a human lifetime. There would be no weather, no open sky, no silence beyond machinery. Research on long-duration isolation from Antarctic expeditions to extended stays on space stations shows consistent patterns. People experience sleep disruption, mood deterioration, heightened interpersonal conflict, and difficulty maintaining motivation over timescales of months. A year in isolation produces serious psychological strain even with regular communication back to Earth. Remove the communication. Extend the duration to a lifetime. Extend it to many lifetimes. A generation ship is the theoretical solution. A vessel large enough to sustain a complete ecosystem, with enough genetic diversity in its population to prevent inbreeding collapse, and with a culture specifically designed to maintain mission continuity across centuries. Children would be born on the ship, live their entire lives on the ship, and die on the ship, passing the mission to the next generation. Their grandchildren might be the ones who actually decelerate into the Proxima system. The engineering requirements for such a vessel are extraordinary. Every nutrient in the food supply needs to be produced internally. Water must cycle through closed loops with zero net loss. Air composition must be maintained precisely without drawing from external reserves. Every mechanical system must be repairable with materials already on board, because ordering replacement parts from Earth would take 4.2 years at the speed of light just for the request to arrive, and another 4.2 years for anything sent in response. The mission would need to be completely self-sufficient, a sealed world within a world, crossing the dark between stars. No government has funded serious engineering studies on generation ships. No space agency has committed to even early-stage research on the life support systems such a vessel would require. The concept exists in theoretical physics papers and science fiction, with the gap between those two categories remaining essentially uncrossed. 75,000 years. In the dark. And even that assumes a straight shot with no engine failures, no meteor strikes, no catastrophic life support collapse, and no breakdown of social order across dozens of consecutive generations. A generation ship would carry more than people. It would carry an entire civilization. Every system that allows a community to function over centuries would need to exist within the hull. Legal systems for resolving disputes. Educational institutions for passing knowledge to children who were never taught by external schools. Agricultural systems for producing enough food variety to prevent nutritional deficiencies across lifetimes. Medical systems capable of handling every illness from a broken bone to cancer without access to external hospitals or pharmaceutical supply chains. Governance becomes a central challenge. A mission launched with a specific goal by the generation that built the ship would need mechanisms to ensure that goal remains the priority 300 generations later. History on Earth shows how completely institutional priorities shift over centuries. Religions have transformed into something unrecognizable over comparable timescales. Governments have risen and collapsed. Languages have mutated into entirely new ones. A generation ship crew living for 75,000 years would develop a culture as alien to the founders as modern English speakers are alien to whoever spoke the ancestor of language 100,000 years ago. They would have a different religion likely invented on board, different social customs, possibly a different spoken language, a different understanding of what the mission even means. Maintaining the technical knowledge required to keep the ship functioning presents a parallel problem. Every engineer who built the original systems eventually ages and dies. Their replacements need to be trained by those engineers before they go. This apprenticeship chain needs to hold unbroken across thousands of generations. A single gap, one period where the relevant knowledge fails to pass successfully to the next cohort, could mean systems fail without anyone on board understanding how to repair them. Historians studying ancient civilizations have documented exactly this kind of knowledge collapse on Earth. Techniques for building Roman concrete were lost after the fall of the empire and only recently rediscovered by analyzing surviving structures. If concrete mixing knowledge can disappear within a few centuries on a connected planet with millions of people, the probability of maintaining spacecraft engineering knowledge across 75,000 years in a closed system of a few thousand people approaches something very close to zero. Genetic diversity compounds the problem. A founding population small enough to fit on a spacecraft would face serious inbreeding pressure within 10 to 15 generations unless reproduction was actively managed to maximize genetic mixing. Managed reproduction across that many generations begins to resemble something that raises deep ethical questions about consent and autonomy. The thought experiment of a generation ship arrives quickly at its limits. Every solution requires another solution. Every system requires another system. The complexity compounds until the engineering challenge feels less like building a spacecraft and more like building a small independent civilization, robust enough to last longer than ancient Rome lasted by a factor of several hundred. And at the end of 75,000 years, the crew that arrives, so distant genetically and culturally from the founders that they share only the mission itself as heritage, would decelerate into the Proxima system and find a planet that may or may not be what the original scientists hoped it was. The answer to whether it was worth the journey would reach Earth at the speed of light. In 4.2 more years after arrival, over 75,000 years after departure, suppose engineers cracked the propulsion problem. Suppose a spacecraft could accelerate to a significant fraction of the speed of light, 10%, 20%. At those speeds, the journey to Proxima Centauri shrinks from 75,000 years to something closer to 10 to 40 years from the crew's perspective. That would seem to solve everything. It does not. At speeds approaching the speed of light, the universe enforces a rule called time dilation. And time dilation turns any relativistic journey into something far stranger than a simple fast trip. Albert Einstein's theory of special relativity, confirmed repeatedly by experiment over more than a century, contains a specific prediction: time does not pass at the same rate for all observers. A clock moving at high speed ticks more slowly than a clock sitting still. The faster the clock moves, the more slowly it ticks relative to a stationary observer. At everyday speeds, this effect is too tiny to notice. At 10% of the speed of light, it is small but measurable. At 50% of the speed of light, it becomes significant. At 90% of the speed of light, time for a moving crew passes at less than half the rate it passes for someone stationary back on Earth. Here is what that means for a crew traveling to Proxima Centauri b. A spacecraft traveling at 90% of the speed of light would reach Proxima Centauri b in about 4.7 years from Earth's perspective. Since the star is 4.2 light-years away and the spacecraft cannot quite cover that in 4.2 years at 90% speed, but the crew aboard, with time passing more slowly for them, might experience only about 2 years of subjective time during that same journey. They arrive, they explore, they send a signal home confirming what they found. That signal travels back to Earth at the speed of light, taking 4.2 years to arrive. The total round trip in Earth time from launch to receiving the signal is nearly 9 years minimum. In the crew's experienced time, it might feel like 6 or 7 years. That sounds almost manageable, but consider what happens at even higher speeds. At 99% of the speed of light, the crew might experience only months of travel while years pass on Earth. At 99.9%, the distortion becomes extreme. Long journeys feel short for the crew, while decades or centuries tick by on Earth. A crew returning from a distant target at relativistic speed arrives back on Earth into a future they did not experience. Their friends are older, their families might be gone. The world has changed in ways that feel sudden to the crew but took years or decades to unfold for everyone else. Every relativistic explorer is a time traveler in one direction. They age slowly while the universe ages fast around them. Returning home means returning to the future. That trade-off is physics, not a story problem. It applies regardless of the propulsion technology used. Accelerate fast enough to reach distant stars in a human lifetime, and the price is disconnection from the area you left behind. The universe offers speed, but it charges something irreplaceable in return. Picture a crew of 12 people launching from Earth toward Proxima Centauri b. Their spacecraft uses some future propulsion system capable of accelerating to 90% of the speed of light. From Earth's perspective, the journey one way takes about 5 years. From the crew's perspective, aboard a ship where time moves more slowly, the journey feels like roughly 2.5 years. They arrive. They study the planet from orbit. They send probes to the surface. They gather data on the atmosphere, the radiation levels, the geology. They spend 2 years conducting the most important scientific mission in human history. Then they begin the journey home at the same speed. The total trip from Earth's perspective lasts about 14 years. From the crew's perspective, accounting for time dilation, the round trip feels like about 7 years. They return. They land. They step out of the spacecraft expecting to see the world they left behind, aged by 7 years. The world they find has aged by 14. Their children are 7 years older than expected. Anyone who was elderly when they departed has likely died. Technology has advanced through another decade of development. Political situations have shifted. Some of their colleagues in the space program have moved on to other careers or passed away. For the crew, the gap feels sharp and sudden. For everyone on Earth, the crew's absence lasted 14 years, and the world simply continued without them. The crew members are time travelers, not in the dramatic science fiction sense, but in a real, documented, physics-confirmed sense. They compressed their own time, while the universe kept its own schedule. This effect gets more extreme the faster the spacecraft goes. A crew traveling at 99% of the speed of light to a star 10 light-years away would experience a journey of about 18 months, while 20 years pass on Earth. They return to a world 2 decades older than the one they left, after less than 2 years of their own experienced time. The psychological implications are significant. Astronauts returning from 6-month stays on the International Space Station report difficulty readjusting to normal life on Earth. The world moved forward while they were gone, even by just 6 months. Relationships shifted. News accumulated. Life did not pause. Multiply that by a factor of 2, 10, or 100 in terms of time discrepancy, and the readjustment problem scales accordingly. Every deep space explorer at relativistic speeds would return to an Earth that has moved further ahead without them. There is no practical way to avoid this. The physics does not offer a loophole. Travel fast enough to reach distant stars in a human lifetime, and the cost is returning to a future that belongs to strangers. Some researchers have suggested that relativistic explorers would need to think of the mission as one way from a social perspective. Even if the spacecraft returns, the home they return to is not the home they left. Moving at a significant fraction of the speed of light turns the vacuum of space into a shooting range aimed directly at the spacecraft. Space looks empty. Between stars, the density of matter drops to extraordinarily low levels. But low density is not zero density. Interstellar space contains gas molecules, mostly hydrogen, and microscopic dust particles. At slow speeds, these particles pose no meaningful threat. A grain of dust smaller than a human hair, encountered at a few thousand miles per hour, barely registers as a physical impact. At 10% of the speed of light, that same grain of dust carries the energy of a small explosive. At 20% of the speed of light, it hits with the force of a rifle round. At 50% of the speed of light, a single microscopic particle impacts with enough energy to punch through thick metal shielding. A spacecraft crossing the interstellar medium at relativistic speeds would encounter millions of these particles along a journey of 4+ light-years. Most of the particles are single hydrogen atoms, far smaller than dust. But even hydrogen atoms at those speeds carry enough kinetic energy to damage hull materials and electronics over time. Engineers studying this problem have proposed several solutions. A magnetic field surrounding the ship could deflect ionized particles, since charged particles follow magnetic field lines and can be steered around the hull. This would handle the hydrogen gas effectively. Uncharged dust particles would not respond to magnetic fields. A physical shield made of extremely dense material placed at the front of the spacecraft could absorb impacts. The shield would gradually ablate, eroding as it absorbs hit after hit over years of travel, but it could be designed thick enough to survive the journey. The downside is mass. A shield dense enough to protect against relativistic dust impacts would add enormous weight to the spacecraft, and weight is the enemy of every propulsion system ever designed. Some engineers have proposed using a cloud of water or liquid hydrogen ahead of the ship, sprayed out to absorb incoming particles before they reach the hull. The spray itself gets stripped away by impacts, but it shields the more valuable systems behind it. Every proposed solution adds complexity, mass, or energy requirements. Every addition makes the propulsion challenge harder. Getting a spacecraft to 10% of the speed of light requires a staggering amount of energy. Getting a shielded spacecraft to that speed requires even more. The shielding problem alone may limit practical interstellar travel speeds to levels well below what time dilation studies suggest would be useful. There is a sweet spot, if one exists, between fast enough to arrive in a reasonable time and slow enough that the dust and gas encountered along the way does not destroy the ship. Finding that sweet spot requires information humanity does not yet have. The density and composition of the interstellar medium between our solar system and Proxima Centauri has been partially measured but not fully mapped. The precise hazard level depends on details that only a probe actually crossing that space could confirm. The first probe sent toward Proxima Centauri B would face these risks without any prior data from the specific route. Every system on board would be a test, with no rescue or repair available from Earth, and a signal delay of over 4 years for any communication in either direction. In 2016, a group of scientists and engineers announced a project called Breakthrough Starshot. The concept abandoned everything about traditional spacecraft design. No rockets burning for minutes, no massive fuel tanks, no crew, no life support, no communication dish the size of a building. Instead, Breakthrough Starshot proposed sending probes the size of postage stamps. The light sail design calls for a chip carrying basic instruments, camera sensors, communication equipment, and navigation systems, all miniaturized to fit on a surface a few centimeters across and weighing only a few grams. Attached to this chip is a reflective sail, also tiny, designed to catch light the way a regular sail catches wind. The propulsion system would not be on the spacecraft at all. It would be on the ground, on Earth. An array of powerful lasers, potentially spanning several miles and combining into a single focused beam of extraordinary intensity, would fire at the sail as the probe leaves Earth's orbit. The pressure of the laser light pushing against the reflective sail would accelerate the tiny probe to extraordinary speeds. Within minutes, the target speed is 20% of the speed of light. At that velocity, the journey to Proxima Centauri B takes about 20 years. 20 years, not 75,000, not 20. For the first time, a proposal put a journey to our nearest stellar neighbor inside a single human lifetime. The engineering challenges are serious but at least theoretically solvable, unlike the propulsion challenges facing conventional rocket designs aimed at the same target. The laser array would need to deliver enormous power to the sail during the acceleration phase. The sail itself would need to reflect that energy efficiently without absorbing it as heat and melting. The chip would need to survive the acceleration forces, which during the laser burn would reach tens of thousands of times Earth's gravitational pull. All of that needs to happen with hardware too small and light to carry heavy shielding. And then comes the dust problem discussed earlier. A chip traveling at 20% of the speed of light needs some kind of protection from the interstellar medium, but it cannot carry heavy shielding without defeating the purpose of being lightweight. The biggest practical limitation is one the designers acknowledged from the start. The probe arrives at Proxima Centauri B at 20% of the speed of light. There is no braking system. There is no way to slow down. The probe flies through the Proxima system in a matter of hours, cameras firing continuously, collecting as much data as possible before the star system vanishes behind it, and the probe continues into deep space forever. 20 years of travel for a few hours of observation. Every image, every measurement taken during that brief flyby, transmitted back to Earth at the speed of light, arriving 4 years after the flyby itself. 24 years after launch, humanity might see the first close-up data from the nearest potentially habitable world ever confirmed. in blinks of time compared to any other proposed method of reaching it. Breakthrough Starshot remains in early development phases, with significant engineering problems unsolved. But the core physics works, and a physics-valid concept is a starting point. Imagine the probe arrives after 20 years of crossing the dark between stars. The tiny chip and its tattered sail enter the Proxima Centauri system, traveling at 20% of the speed of light. At that speed, covering a distance equal to the gap between Earth and our Moon takes about 2 seconds. Covering the distance from the outer edge of the Proxima system to Proxima Centauri b takes only a few hours. The cameras fire from the moment the probe enters the system. Every sensor records continuously. The star grows from a point of light into a dim red disk. Proxima Centauri b grows from an invisible dot into a resolved sphere. What would those hours reveal? Possibly an ocean, possibly bare rock, possibly a thick atmosphere that bends light around the planet's limb as it passes. Scientists would look for color variation across the surface, blue suggesting liquid water, brown or red suggesting bare land, white suggesting ice or cloud cover. They would look for the chemical signatures of gases in the atmosphere, which would show up as specific patterns in how the planet absorbs different wavelengths of light. And then the planet would be gone. Past. The probe continues outward at 20% of the speed of light, leaving Proxima Centauri behind in minutes. The system recedes. The red star shrinks again to a point. The interstellar medium swallows the probe as it heads toward whatever lies beyond. The data compressed and encoded would travel back toward Earth as a laser signal, moving at the full speed of light. 4.2 years later, those signals would arrive at receiving stations on Earth. Scientists would decode them, process the images, analyze the spectra, and either confirm or deny everything humanity has theorized about Proxima Centauri b for decades. That result, whenever it arrives, would be the most consequential scientific data ever collected. Confirmation of an atmosphere would be extraordinary. Confirmation of water features would be staggering. Any chemical signature associated with biological activity, oxygen, methane, or other gases that chemistry alone cannot easily produce in the right combination, would be something beyond any category of discovery in human history. And humanity would watch all of it happen from 4.2 light-years away, receiving the images years after the probe flew past, unable to send a follow-up, unable to zoom in on anything interesting spotted during the flyby, unable to stop the probe and take a second look. One pass, a few hours, then silence. Every question Breakthrough Starshot could answer would generate dozens more that could only be answered by something that could slow down and stay. And slowing down requires a braking system. A braking system requires mass. Mass requires more energy to push. And the cycle loops back to the beginning. The universe gave us a nearby candidate and a physics framework that makes reaching it theoretically possible. Then it arranged the arrival in a way that makes any meaningful study almost impossible. Every plan to reach another star runs into the same wall. Energy. Sending a postage stamp probe to 20% the speed of light using Breakthrough Starshot's laser concept requires a laser array delivering roughly 100 gigawatts of power during the acceleration phase. 100 gigawatts is approximately the total electricity generating capacity of a small country, all of it focused into a beam and fired at a tiny reflective sail for a few minutes. That energy requirement for a chip weighing a few grams sounds extreme. Now consider what it would take to send something with mass. A small robotic probe weighing 1 kilogram, roughly the weight of a liter of water, would require approximately 10,000 times more energy to accelerate to 20% of the speed of light. The laser array needed to launch, it would have to be so powerful that it could not currently be built anywhere on Earth. A crewed capsule weighing even a modest 10 metric tons would require energy equivalent to every power plant on Earth, running continuously for years just for the acceleration phase. The numbers stop being engineering problems and start being physics arguments. Chemical rockets, the technology used for every crewed spaceflight in history, cannot approach these speeds regardless of design. Chemical reactions release a fixed amount of energy per unit of fuel. The most energetic chemical reactions known deliver enough energy to push exhaust at speeds far below what interstellar travel requires. Nuclear fission, the process inside nuclear power plants, delivers dramatically more energy per unit of mass than chemical reactions. Theoretical nuclear pulse propulsion designs, which use small nuclear detonations behind the spacecraft to push it forward, could reach speeds of 1 to 3% of the speed of light, better than Voyager. Still means a journey to Proxima Centauri b takes roughly 200 to 600 years. Nuclear fusion, the process that powers stars, offers still higher energy output per unit of mass. Engineers have worked on fusion propulsion concepts for decades. A fusion-drive spacecraft might reach 5 to 10% of the speed of light. The journey shrinks to 40 to 80 years. Achievable within a human lifetime? Barely. Antimatter propulsion stands at the theoretical extreme. When matter meets antimatter, the two annihilate each other and convert entirely to energy, the most efficient energy release physically possible. An antimatter drive could theoretically accelerate a spacecraft to a significant fraction of the speed of light, with far less fuel mass than any other concept. The problem is antimatter. Humanity currently produces antimatter in laboratory particle accelerators in quantities measured in nanograms, billionths of a gram. Producing enough antimatter to fuel even a small interstellar probe would require energy input equivalent to the entire output of human civilization for years or decades, using technology that does not yet exist. Every propulsion concept that makes interstellar travel possible within a human lifespan requires technology several generations beyond what exists today. Every concept that uses existing technology produces journey times measured in thousands or millions of years. The energy wall is real. Physics built it. And so far, nobody has found a door. Physics allows some ideas that sound impossible and forbids others that seem straightforward. Warp drives fall into the complicated category. In 1994, physicist Miguel Alcubierre published a mathematical solution to Einstein's equations that described a spacecraft moving faster than light by distorting space itself. Rather than moving through space, the spacecraft would sit inside a bubble of compressed space in front of it and expanded space behind it. The bubble would move, carrying the ship along, while the ship itself never technically exceeded the local speed of light inside its bubble. The mathematics works. The physics of general relativity technically permits this solution. The engineering requirements are another matter entirely. Creating an Alcubierre warp bubble requires a form of energy called negative energy, which pushes outward rather than pulling inward like normal gravity. Negative energy exists in quantum mechanics in very small amounts, confirmed by experiments. The amount required to create a warp bubble, large enough to contain a spacecraft, was originally calculated at a quantity greater than the total mass energy of the observable universe. Later refinements of the mathematics reduced that requirement significantly. Researchers have proposed geometries of the bubble that bring the energy requirement down to merely the mass energy equivalent of a large planet. Still impossible to produce, but conceptually closer to something that might one day be within reach of a civilization far more advanced than ours. Wormholes present a similar story. General relativity permits mathematical solutions that describe tunnels through space-time connecting two distant points. Step into one end, emerge from the other, potentially light years away in a fraction of a second. The mathematics is valid. Keeping a wormhole open requires exotic matter with negative energy density. Same problem as the warp drive. The quantities required exceed anything humanity can currently produce, or even conceive of producing with known physics. Then there is the question of whether faster-than-light travel, if achieved by any method, would violate causality. Causality is the principle that causes happen before effects. Certain interpretations of relativity suggest that moving information or matter faster than light between 2 points would allow, under some reference frames, effects to precede their causes. This would break the logical structure of the universe in ways that most physicists consider deeply problematic. Some researchers argue that any valid theory of faster-than-light travel must somehow preserve causality. Others argue that causality might be a larger principle that the universe enforces in ways not yet understood, preventing faster-than-light travel precisely because it would otherwise create paradoxes. The honest answer is that faster-than-light travel remains in the category of things physics does not forbid, with absolute certainty, but also provides no practical path toward. The gap between theoretically permitted and actually buildable is the entire gap between now and some future civilization, so advanced it would be unrecognizable to anyone alive today. Until that future arrives, the distances stand, the stars stay where they are, and every twin world identified by every telescope ever built remains on the other side of a wall humanity has never crossed. Humanity lives on a planet surrounded by a prison it cannot see. The walls of this prison are not made of metal or energy fields. They are made of distance and time and the hard limits of physics. Every star system beyond our own sits behind a barrier that even the fastest things ever built by human hands cannot cross in any meaningful time frame. This situation has a name among scientists who study it seriously. They call it the cosmic quarantine. The idea is that any life in the universe, regardless of intelligence or technology level, faces the same fundamental challenge. Stars are far apart. Moving between them requires either enormous time or enormous energy, and both of those requirements scale in ways that make interstellar civilization nearly impossible with any technology that obeys known physics. The quarantine applies equally in all directions. Any civilization in the Milky Way faces the same distance as we do. If intelligent life exists on Proxima Centauri b, or Kepler 452b, or any of the thousands of confirmed exoplanets orbiting nearby stars, those civilizations are just as trapped as humanity. This idea helps explain a puzzle called the Fermi paradox. The galaxy contains hundreds of billions of stars, many with planets, many inhabitable zones, some around stars that have burned stably for billions of years longer than ours. Statistically, the probability that intelligent life evolved somewhere else in that enormous collection of worlds seems high, and yet no confirmed signal from any extraterrestrial civilization has ever been detected. The galaxy appears silent. The cosmic quarantine offers one answer. Civilizations do develop. They look up at the stars. They find their neighboring worlds interesting and possibly inhabited. They attempt communication by sending signals at the speed of light. Those signals take hundreds or thousands of years to arrive. Any response takes just as long to return. A conversation with a civilization 400 light-years away operates on an 800-year round-trip delay, and physical travel between civilizations remains essentially impossible with any technology that obeys the energy and speed limits built into the universe. The quarantine is not malicious. The universe did not design it to trap life. Distance is simply a consequence of how a universe, expanding from a single point, distributes matter across enormous volumes of space. Gravity clustered matter into stars and planets, but the clusters sit far apart by the standards of any species trying to move between them. Earth holds one piece of evidence about what the quarantine means in practical terms. Every person who has ever lived, every civilization ever built, every event in all of recorded human history happened on a single rock about 8,000 miles across. Every war, every discovery, every piece of music and art and mathematics ever created emerged from one world. The nearest confirmed potentially habitable world sits a distance away that makes every human journey ever completed look like taking a step backward compared to running to the moon. The quarantine is why this matters. Every resource on Earth is the only resource accessible. Every species here is the only species protected. Every problem that could end human civilization has no backup planet to escape to. Venus is hostile. Mars is harsh and distant in energy terms. The nearest twin is 4 light-years of impossible travel away. Home is not a starting point. For now, it is the only point there is. Finding an Earth twin and reaching an Earth twin are completely separate achievements. Humanity accomplished the first one. Telescopes confirmed worlds that match Earth's size, orbit, and stellar neighborhood. Kepler 452b passed more tests than any exoplanet before it. Proxima Centauri b sits at the nearest star. The confirmation is real, built on repeated observations, multiple methods, years of analysis. The second achievement belongs to a future so far removed from the present that imagining the technology required involves imagining a civilization that no longer recognizably resembles ours. But that gap between finding and reaching is precisely what makes the search meaningful. Every confirmed exoplanet represents more than an entry in an astronomical catalogue. Each one is proof that the conditions required for life as known on Earth are not unique to this world. Rocky planets in habitable zones orbit yellow dwarf stars throughout the galaxy. The ingredients exist elsewhere. The recipe has been followed elsewhere. Whether the result includes life is a question the universe has not yet answered for us, but the raw materials are clearly present in multiple locations. That knowledge changes something fundamental about the human position in the cosmos. For most of human history, Earth appeared to be singular, special, possibly the only world of its kind. The assumption was not arrogance so much as ignorance. There was no data. Now there is data. And the data says Earth is almost certainly not singular. The type of world Earth is rocky, water-bearing, in a habitable zone around a stable star, appears to be common throughout the Milky Way. Estimates built on Kepler's survey data suggest tens of billions of potentially habitable rocky planets in the galaxy alone. The observable universe contains roughly 2 trillion galaxies. The scale of that possibility is itself staggering in a different direction from the scale of the distances. There is an enormous amount of universe, and a significant fraction of it appears to contain the conditions required for chemistry like Earth's. The distance problem and the abundance of candidates create a specific tension. Everywhere worth looking is unreachable. Every interesting target sits behind a wall of light years. Every path forward requires either technological leaps that current physics does not clearly permit, or timescales that exceed the plausible duration of any single civilization. Proxima Centauri b, at 4.2 light-years away, is the closest candidate, and it requires 75,000 years at current speeds. Kepler 452b at 1400 light-years away would take 25 million years. Both of those numbers point to the same conclusion. The next chapter of the human story, whatever it contains, plays out on Earth. Asteroid mining might extend resources. Mars might become a second foothold. The outer solar system holds massive amounts of raw material, but another Earth, another planet that could independently support a large population of humans, sits behind a barrier that humanity has so far found no way to cross. The universe placed its most valuable locations behind its largest locks. It confirmed that twins of Earth exists throughout the galaxy, then arranged those twins at distances that make visiting them the single hardest engineering challenge conceivable. That challenge is real, the distance is real, the twins are real, and humanity, for now, watches all of it from one small rock, 4.2 light-years from the nearest candidate, carrying every hope and every person and every unfinished story forward on the only world it has.